Good afternoon, everyone, and welcome to the program of Tea Time Technical Talks organized by DFI Middle East. This program is a series of technical seminars that will be offered every first Tuesday of every month. Today will be the first seminar, and we are delighted that this seminar has been prepared by one of the legends of geotechnical engineering, Professor Bengt Fellenius, on static loading test performance, instrumentation, and interpretation. Unfortunately, Professor Fellenius was unable to deliver this seminar himself, mainly because of the time zone difference between us and where he lives in Canada. And I am delighted that he has kindly accepted that I will deliver the seminar and the presentation on his behalf. So I hope that I will do my best actually to highlight all the ideas that he wanted to present today. But definitely Dr. Fellenius will be very happy personally to follow up on the concerns of any of you by email directly. So if you have any questions after the seminar, which I will not be able maybe to clarify, it will be directly delivered to Dr. Fellenius for his feedback. Of course, a few words about Dr. Fellenius. He is, of course, a very well-known professor, formerly professor of civil engineering at the University of Ottawa, is an internationally recognized foundation engineering consultant and the author of more than 400 technical papers. His professional experience comes from a wide variety of assignments that encompass foundation design for industrial plants, water and sewerage treatment facilities, bridges and highway projects, marine structures and urban area development, as well as participation in special investigations, instrumented field tests, etc. Dr. Fellenius has given lectures and courses to several universities and international conferences throughout America, Europe, and Southeast Asia. He currently lives in Sydney, BC, Canada. I am Emad Sharif. I'm working as the Director of Geotechnical Testing Consultants, GTC, in Dubai, and I'm a member of the committee of DFI Middle East. The seminar is about the static loading test, performance, instrumentation, and interpretation. And the main topics or contents that will be covered by the seminar is, first of all, is to give the problem of defining the axial load capacity of a single pile, and then to highlight the main advantages of the use of instrumented static pile loading tests, give some guidelines on the procedure and interpretation of instrumented pile load tests, then to highlight also the importance of defining the non-TZ and QZ curves, their definition and application for proper simulation of the results of static loading tests. Then we will give some focus on the bidirectional or all-cell static load test, the components, procedure, and interpretation. And we'll present a few case histories depending on the time available. So this seminar is planned to be between 40 minutes to 50 minutes, hopefully, of the main presentation. Then it will be followed by a questions and answers session. You can write your questions on the chat box so that we can look at this at the end of the seminar. First of all, talking about the static load test capacity. This is a routine static loading test, provides the load movement of a pile head and the pile capacity has to be defined. And the curve that you can see on the screen, it shows the curved pile head movement versus load as we obtain from a conventional static load test. And the question is how we can define the capacity of the pile. What is the definition? Where is the point that we will locate on the curve that will define the capacity of the single pile? And as you can see on the screen, there are several methods known in literature, ranging from Davison rule to Fuller to Chain-Condner, Brinch-Hansen, Didier, etc. And every one of these methods has its own analytical procedure, but it will give a different definition of the axial capacity using the same data. And this is a problem usually in our literature. And still also, the definition that is used still in many of the specifications is the so well known, or the criteria that is belonging to Terzaghi is about the 10% diameter movement of the pile, where this can be also defined on such a curve. So the point is that the definition of capacity of a single pile is not well defined in geotechnical literature. The decisive value of assessing the suitability of a pile to safely support a structure is the movement that the supported structure can accept without distress, not a capacity chosen as a specific load derived from the shape of or a point on the load movement curve. Yet, the latter is the most common approach to assessing the suitability of a pile for use in supporting a structure. And this is the problem that we have. We have always to define a capacity of the pile, but still the capacity definition is not well defined. According to Dr. Fellenius, it is the displacement or the settlement of the pile where the structure can tolerate without distress is what we should be looking after. However, we are still important to define a capacity of a pile from its loading test behavior. These are some of the data that has been available from events that were organized to try to check the definition of the capacity of a pile from pile load test data. This slide shows the results of what is known as Arquari prediction in 2015. This event was held in Brazil, and the shown load test curve was distributed to many of the participants to define the pile capacity based on their experiences and based on their the different criteria that they are using in their practical experiences. And the results came as presented here, that we have 29 participants has replied to the question to give the capacity prediction. And it turned out that the effort is no longer a prediction of the capacity, but is an assessment with the participants applying their usual method for determining capacity developed in a static loading test. So as you can see here, the predictors or the assessors has found that the capacity for this pile ranged from 6,000 kilonewton to more than 8,000 kilonewton, which is a very large variation for the same pile load test data. So the problem of defining the capacity is very obvious. Indeed, the profession does not have a common definition of capacity. We have different methods, approaches, but not a single definition of capacity. Another example is the prediction event in Bolivia, which was held in May 2017, where also the assessors from different places over the world, 94 individuals has been participating in this event, and the shown pile load test curve was distributed. And as you can see, the results also show very big variation in the assessment of the capacity of the pile, and a very big statistical deviation also is indicated. So therefore, once we want to define capacity of a single pile from a load test data, we must be careful for giving the definition of how we are going to do that. And this is why the importance of instrumented load test comes into the picture. So according to the definitions, or the conclusion of Dr. Fellenius, the capacity is a mem, a thought package in our mind, replicating itself as it burrows deep into our unconsciousness, forever requiring us to feel it. So here, determining the force by means of a strain gauge. Now, the use of instrumentation or strain gauges instrumenting the pilot test or the static pilot test give the opportunity to determine the forces distributed in the pile shaft and improves our understanding of the behavior of the pile. So nowadays, use of vibrating wire type strain gauges, and sometimes the electrical resistance gauges are still used. Okay, it's very well established, and many companies are producing accurate types of vibrating wire, and which are also commercially feasible for accurate and reliable means for determining the force imposed in a test pile. However, it is unwise to cut corners by field attaching single strain gauges to the rebar cage. Always install factory assembled sister bar gauges. In the next slide, we'll show photographs of what we mean by sister bar gauges and factory assembled systems of strain gauges. Lately, fiber optical cables known as DFOS have been used to obtain an almost continuous profile of induced strain. As of now, however, the cables are temperature sensitive and readout unit is expensive. They should always be installed in pairs, 2 cables, and the data need to be correlated to measurements from conventional vibrating wire gauges. So therefore, still the use of optical cables is not put into commercial practices, maybe in some research works, because it can give a continuous record of the strains, not only at discrete levels as we usually do. Other instruments other than the vibrating wire gauges are the retrievable extensometers. They are used in some projects, but the most common types of strain gauges are now the vibrating wire types. The gauges must be installed in pairs that are placed diametrically and equidistantly from the pile center, and not as single units, nor as 3 asymmetrical locations, okay, which will be illustrated in the next slide. This is a very, very important guideline about how we plan our instrumentation for the. First of all, this photograph shows what we mean by the sister bar, company or supplier assembled sister bar. So here we have the strain gauge is assembled to a separate extra bar that can be fixed along the rebar on the steel cage, okay, and can be tied to it. It has sufficient length so that it can develop the load, and sometimes it can be welded, and it comes with different range of diameters suitable for different applications. In local practices, sometimes we are only using the embedded type strain gauge, vibrating wire strain gauge, and we just tie it to the steel bar like this. This method is, the strain gauge is subject to tilting, displacement, and sometimes to damage. So the state-of-the-art instrumentation is to use factory supplied sister bars, because we are looking for accurate simulation of the pile behavior, and there is no means of reducing few expenses of the expenses test itself. Now, in many cases, once the load is applied to the static during the static pilot test, there will be a kind of bending effects at different levels. Bending may result from the deviation from verticality, change of the cross section, and other reasons, and therefore the strain gauges which are installed at certain levels or at specific levels along the pile shaft must be placed in pairs. Pairs means that we have a strain gauge, for example, at level 1. They are installed like 4 strain gauges along the cross section, A, B, C, and D, where A and C are on 1 diameter, B and D are on the other diameter. So we have pairs of strain gauges. In the example that shown on the slide, the strain versus load relations or data is plotted, and it shows that we have very limited deviations or variations between the data gathered by the different strain gauges, and accordingly, this shows that we have little or no bending effects. However, in other cases where bending effects exist, we will see that A and C, which are pair of strain gauges located on the same diameter, but each one is showing different, range of strains. Okay, and also B and D are also showing different range. So if we combine A and C together, then we get a good average. If we combine B and D together, then we get a good average. If we combine the four results together, we are getting a good average because this will cancel the effect of bending. Okay. However, what happens if one of the strain gauges was bad or was dead? So in this case, okay, both pairs of curves from pile 2 indicate bending. Averages are very close, essentially the same for the two pairs. Okay. However, both sets of records for piles 1 and pile 2 are good and fully useful. However, what would happen if one or two gauges turn out to be bad or even dead? And this is explained here. So here, if we want to combine three of the gauges, so I have here A plus C plus D, or A plus C plus B, or two strain gauges that are not pairs. So I select, instead of AC, I took A and D, which are on different diameters, or B and C. So all these selections will be poor. All these selections will give me data that is not representing the actual behavior because of the effect of bending. So in this case, if any of the strain gauges gave bad data or it was dead, then we have to cancel the other pair. So I can cancel A and C, okay? I can give the average of A and C, or B and D, or the four together, but I cannot combine any three of them because it will shift the measurements to a wrong position, as we see from the curve. So there will be a big error based on the amount of bending. But this as a guideline, then in our testing, we must ask, the reporting company or the company who's doing the test to present such data, to give these data about the strain and load information, so we can see, the response of each strain gauge and how the averages has been taken, because the averages are then used to calculate the load at every level, as we can see now. So now we measure the strain. So here, with the guidelines given, we know that we are now getting reliable measurements of the strain at different levels, but we are not interested in the strain. We are interested to know the stress, or we are interested to measure the load. So how we get this, we have the strain, how we get the force. So we need to know the force. So if we look at the relationship between strain and stress, then we multiply this strain by the modulus, we get the stress, and we multiply by the cross-sectional area, we get the force. And therefore, the term EA, which is the axial stiffness of the pile, is a key parameter. Okay? So here we must focus on how we can get accurate estimate or accurate assessment of EA in order to get the force at different levels. And here is the situation. So if we are dealing with the concrete piles, then we are talking about combined material. We have concrete, we have steel, sometimes we have casing. If we are talking about steel piles, only steel piles, then the modulus is ES, and it is almost linear. It is less dependent on the strain, and the area, cross-sectional area, is well defined, so there is no great deviation. But when we are talking about board piles, about concrete piles, then we are talking about steel and concrete, and generally equations like this can give us the combined modulus of the cross section. However, we know that ES is the steel modulus, it is very accurately defined, and the area of steel is also very accurately defined, whereas the area of concrete and the modulus of concrete is less accurately defined, less accurately given. Okay, so ECAC, this term is less accurate, and in this case, we have to see what we can do about it. So if we plot again from the results of instrumented pilot test, okay, if this is the average strain at a certain level, and this is the load applied, and here we have to select the level that is not affected by the shaft friction. So if we are doing a top-loaded pile, we select the upper level where the strain gauges are installed, which is close to the applied load, applied to the top of the pile in this case, so that the effect of shaft friction within half meter or so is very, very less, and therefore the applied load is known from the jacks, from the applied hydraulic jacks, and the strain is measured by the strain gauges. Then we can plot the relation, and we get the blue curve, which is a curved relationship in general. This curved relationship allows us, in this case, to find the dependency of the modulus, of the secant modulus, and the strain. So at any point, we can take this secant modulus, ESA, we plot load versus strain, then the slope is ESA, so this is the secant modulus, or we can draw the chord between any two different load levels, so Q1 and Q2, so delta Q over delta epsilon will give me ET over EA over A. So ET is a tangential modulus. Actually, this is a chord modulus, but it gives another method. So we can predict, or we can show the modulus of the cross section, or the stiffness of the cross section in terms of secant stiffness, or in terms of tangential stiffness, or incremental stiffness, in other words. Okay. Now, if we plot the relationship between the stiffness ESA versus the strain, we get a straight line. And the slope of the straight line is small a, and the intercept is b. So the formula for this straight line is ESA, which is the secant stiffness, is equal to a constant b, which is the initial stiffness at very small strain, okay, minus the slope times epsilon, which is the strain measured. So this gives you the dependency of the secant stiffness with the measured strain. Or we can also express that in terms of the tangential modulus. And in this case, we will see that the slope of the tangential stiffness curve or line is twice the slope of the secant stiffness. And we will prove this in the next slides. Okay, so here, once we know ESA and we know epsilon, then we can calculate Q at any level. Okay, so the main thing is that we want to define this formula from the results of the static load test. Of course, as we say, the modulus of steel material is very accurately known. It's like 200 GPa or 207, whatever. But the modulus of concrete is sometimes difficult to define. Of course, there are ranges, known ranges of the modulus of concrete. You see sometimes 30 GPa, 20, 35, etc. And there are some relations relating the modulus to the concrete strength, okay, given by ACI code or other codes. However, the accurate definition, this does not show the dependency on the strain actually. So this gives you just a fixed value, and we know that the concrete strength tested in the concrete cube outside the pile or before completing the pile is maybe very much different from the concrete strength and concrete properties when the pile is constructed. Okay, so it's always important to use the results of the strain gauges and instrumentation to determine the axial stiffness for more accurate assessments. So here, if we determine we know, as we saw from the previous slide, that the tangential modulus is just, the delta sigma over delta epsilon. This is the definition of this modulus, and accordingly, ET is delta sigma of delta epsilon, and we know that this is the formula of the straight line of the stiffness, slope A, epsilon plus B. If we integrate this, over epsilon, then we get sigma is equal to half A epsilon squared plus B epsilon, and we know that sigma is equal to secant modulus times epsilon, so we just substitute, and then in this case we get that ES, which is the secant modulus, is equal to half A epsilon plus B, and this proves that the slope of the line for the secant modulus is just half or 50% of the slope of the tangential modulus. And then once we know this, we can calculate Q also. This is results of pilot test, instrumented pilot test. This is a head-down test, so this is a conventional test. It's 1.83 meter in diameter. It's a steel pile. And for steel, we know that the modulus is less dependent on strain, and it is very well defined. It's almost constant. And here we plotted the gauge, the strain gauges, which are taken very close to the applied load. So the gauges are at 1.2 meter below the pile head, so they are not affected by the shaft resistance. And this is the plot of the secant stiffness, EA, secant stiffness, which is equal to applied load Q divided by epsilon versus epsilon. And here we see that the data is very, very well defining almost a constant modulus, and this is EA from the secant is 46.5 giganewton. Whereas if we plotted the tangential modulus, the tangential stiffness or the incremental stiffness, because it depends on different tangential points or incremental points, so we can see lots of variations, and this depends on the accuracy of gathering the loads. However, it gave almost similar prediction and very low, almost zero slope, and the two predictions are almost the same here, because this is a steel pile. For concrete pile, here is an example of a CFA pile, where this is the pile load test, pile head movement versus load relationship. And we know here there is some initial loading and unloading relation, and this is the blue curve shows the first loading, the first loading, secant, this is the load versus strain, and this is the evaluated secant stiffness. And as we can see, because the curve is the relationship is non-linear, so it is reducing 11.2, 10.9, 10.8, etc. And at the final level, it is 10.4. If we plot again the secant stiffness versus strain and the tangential stiffness versus strain, we can get these relations. And with these relations, we can see here in this case the tangential stiffness. We have very small deviations, which means that the data is very accurately collected by the strain gauges, and we can see that the slope of this curve is just twice the slope of this curve, and this is the relationship that we are looking at. So here, ESA in giganewton is equal 11.5 minus 0.003 microstrain, and this relation can be used to evaluate the loads along the pile shaft. This is an example in Hawaii for a concrete pile. This is a 16.5 inch octagonal pre-stressed concrete pile driven to 60 meter depth through coral, clay, and sand. Here the modulus relations are obtained for the uppermost gauge. And this is what we said, that usually we select the uppermost gauge for a conventional pilot test. Here in this case, it was 1.5 meters below the head, so that it's not affected by the shaft friction. And again, this is the tangential stiffness, which is presented as delta Q over delta epsilon. This is equal to ET over ETA versus strain, and we get this relationship. And if we plot the axial strain, we get excellent relation as well. Okay, and we can see that the slope of this line is twice the slope of this line, which means that we are accurate prediction. And this is the relationship that we are looking at for use in calculating the loads along the pile shaft. This is another example of also a concrete pile, which also the same here. Okay, but sometimes, and this is important point to mention, if we want to measure the secant stiffness, we must start from true zero. But if we want to measure or plot the tangential stiffness, because it is, like incremental stiffness, delta Q over delta epsilon, okay, then in this case, we don't need to start from a real zero strain. But in a secant stiffness, we need to start from a zero strain. Sometimes the strain gauges are loaded initially before the test. And in this case, when we plot the secant stiffness, we see that it is nonlinear. So we have to make some kind of correction to reshift the strains to a zero value. So in this example, okay, the secant line, this is the red one is the secant line from the tangent method. Okay, we apply it here and we see how much correction has to be made. And this is after adding 8 microstrain to each of the strain values, we get the secant stiffness line to be matching with the tangential one. So if we want to use the secant stiffness curve, we must make sure that our strains start from a real zero. If it is shifted from a zero, then in this case, the results will be nonlinear. It has to be corrected. So usually in our practical applications, we depend on the tangential stiffness because it does not depend on where the strain value starts. Here are some important guidelines to ensure that our optimal accuracy and reliability of strain gauge records is obtained. And here what Dr. Fellenius says, in the past, loading tests included series of unloading, deloading the test pile in order, it was thought, to get an appreciation of the distribution of force in the pile. The advent of instrumentation gave a different means for this. However, many kept the unloading, deloading steps in the test schedule. This is unfortunate because the shear response along the pile is different in virgin loading and in unloading as well as in reloading fashion. The effect of unloading, reloading is that the measured strains do not represent the true force at the gauge location. As insight and means develop, we have a tendency to hang on to past details. They are as useless as a tailbone. Unfortunately, while a tailbone does not harm, an unloading, reloading event will adversely affect the ability to accurately back analyze the strain gauge records. We'll see some examples of this. Additional undesirable scheduling aspects are to use load increments of uneven magnitude and load holding durations of different length. For optimum value of the test data, increment should be equal in magnitude and load holding should have equal duration. So here we have a few important guidelines given here to ensure that we have data that can be interpreted properly without being affected by unprepared or unrequired procedural steps like unloading and reloading. This is an example where 600 millimeter diameter and 54 meter long strain gauge instrumented cylinder pile. Okay, and here is the loading cycle. It has the first loop L1 and then the second loop L2, and each one has unloading and reloading. And this is the load versus strain relationship. And we can see that the virgin loading, the 1L loop is the blue one, it's nonlinear. Then we have the reloading 2L, it's just different one. So it gives a different and confusing result to get the axial stiffness of the result. If we plot the secant stiffness of the pile, we can see that the first loop, okay, the first loop, which is the blue one, gave a very suitable relationship, whereas the reloading cycle, because it did not start from a 2-0, it gave a nonlinear curve, which is very confusing and has to be corrected by adjusting the strains, in this case by subtracting 59 microstrain, because it did not start from 0. So we have to deduct some microstrains so that the green curve will become to this dotted curve. And this is why, because we have an unloading reloading cycle. If we also plot the incremental stiffness, the tangent stiffness, we get the same thing. So we have the first loop and we have the second loop, okay? And it's only giving us confusing results. And the second loop is, of course, more stiffer, less dependent on strains, because it's a reloading condition. So the unloading reloading event has severely affected the analysis. In this example, we can see that accidentally this pile load test has experienced some leak of the hydraulic oil of the jack, and suddenly the load was dropped. Then the jack was repaired and the load was reloaded again, and we reached the maximum point, and then we unloaded. And even this small partial reloading, it has severe effect. So here is the load versus strain. This is the first loop. Then we have here reloading again, and then we have a break in the relationship. And if we put the incremental stiffness, we can see this is the first loop, okay? This is the first loop, which gave a nice linear relationship here. But then we have reloading, and then once we reach the curve again, we have reached the same line again. So it needs a lot of interpretation and evaluation. So in general, there is no need for this unloading and reloading. This happened by accident, but in general, in our practice, actually here in the Middle East, in general, in Dubai, unloading and reloading are still specified in many specifications and many projects. According to Dr. Fellenius' experience and his recommendations for instrumented pile load test, it is not necessary at all to include any unloading, reloading cycles. Therefore, to ensure good records, the optimum return to our money invested in testing an instrumented pile, we require reliable zero reference, accurate measurements, absence of disturbances. And these disturbances mean unloading, reloading, varying magnitude of load increments, and non-equal load holding durations. So sometimes you see in some testing that, once the load is reaching some value, then the specifications require to hold the load for 4 hours or 6 hours or 12 hours, then to continue for different durations. This will distort the data gathered by the strain gauges, and it will be very difficult to interpret them and use them for simulation of the pile behavior. So once we ensure that we have accurate, reliable measurements absent from disturbances, then we can go forward for further interpretation by analyzing the friction and in-bearing development functions, which are known as TZ and QZ functions from the load test data, and do a complete simulation analysis of our pile. So this is just a fictitious example, a very simple example, 25-meter long pile, 650 millimeter in diameter, having homogeneous soil with 2,000 kilogram per meter cube density. Pore water pressure is hydrostatic with a water table at 1 meter depth, and the side friction is increasing depending on a constant beta value of 0.3 versus the effective pressure. So this is the side friction, theoretical side friction value, okay? And it is mobilized at 5 millimeter displacement. So once the pile has 5 millimeter displacement along the shaft, the maximum skin friction mobilizes 100%. The side friction mobilizes. So this is a typical TZ curve describing the rate of mobilization of side friction for this example. Now, after reaching the maximum side friction, we have three potential behaviors, either to go in a plastic behavior, like the blue curve, or to go in a softening behavior, the green curve, or to go in a hardening behavior, okay, the red curve. And all of these curves can be simulated by selecting some functions to represent the behavior. Okay, for the end bearing, okay, the ratio function known as Wisdala function is used to simulate the development of the end bearing of this pile at 5 millimeter toe movement. The mobilized load at end bearing for this pile is 1660 kilonewton, which is which corresponds to 5 megapascal. Okay, which corresponds to 5 megapascal. So at 5 millimeter displacement, we have this end bearing, and these are the functions that we know mathematically and can be used to simulate a pile. This is just to show the method of theoretical simulation, because these curves we can just get from the load test. Okay, from the instrumented pile load test, we can get the TZ and we can get the QZ at the end bearing, at the end of the toe of the pile, and we can simulate with proper functions. So assuming that these are the functions that are representing this pile and this soil condition, then we can do the simulation analysis with proper software. In this case, Unipile software is used, but there are other commercial softwares available. And the simulation will give me the side friction development for based on the TZ curve that we have selected, either plastic, softening, or hardening, the toe mobilization versus toe movement, and then the total pile head movement load relationship for the three behaviors. So we have softening, we have plastic, we have hardening. Okay, and this is the point here. Okay, where this corresponds to the target load, where we have beta equal 0.3. So our maximum friction is defined based on that, and our end bearing is 5 megapascal. So this is the point on the curve is here, and we know that after this point, okay, we have different behaviors based on the behavior of the side friction, either plastic, softening, or hardening. And this is the point on the toe, which corresponds to 5 millimeter displacement, where the target toe resistance is mobilized. So all this information we can get from the simulation analysis once we define the TZ and the QZ curves. Not only that, we can also get the load distribution along the shaft at different loading stages. So as if we have strain gauges instrumentation and toe instrumentation. So from these functions, okay, which must be calibrated from the instrumented pile load test, we can get the load distribution as here. So this is, for example, this is for a case of loading of 4,000. This is the end bearing. This is our target load. This is the mobilized end bearing, which is 5 megapascal. Okay, and the side friction is as described by beta equal 0.3. Okay, if we take the load at 6,000 kilonewton here, let me see the previous slide, at 6,000 kilonewton, and we take horizontal line, we can see that the total load is different for the three cases of the side friction mobilization, or the TZ types. And we can enlarge this in this screen here. So the load is 6,000 applied at the pile head. The middle one is showing the plastic behavior. and this is showing the hardening behavior, this is showing softening behavior. For this example, with this weak soil, okay, the difference is not substantial, but in practice, in actual cases, the differences can be very large. So it is important from our load test results to get representative functions for the TZ and QW relations. So it's not only the good measurements that guarantee a good conclusion, but we have to do a good thinking is also necessary to ensure that we are getting good conclusions. And this is an example of that. So here we have results of a static load test on 40-meter long jet-in instrumented steel pile. So this is the relation of unit side friction, is showing this side friction that is mobilized versus depth, okay? And this is the load distribution, okay, at this loading stage, at this side friction. This is the end bearing mobilized load, and this is the, what we can do about this. We can do simulation. If we do simulation, if we generate our TZ functions and QW functions and do computer simulation to simulate the result, then we can get something like these red curves, which are very accurate, very closely simulating the actual behavior, and we can adjust our beta values if we are using beta method for the side friction, okay? And from that, we can draw our side friction mobilization in a nice way, so that we have now a model. This is a simulated model, okay? And this simulated model is accurately matching the actual result of a load test, but on the same time, it is a rational, and it's not dependent on, you know, like one layer by one layer simulation. It is based on more or less on behavioral simulation, which can now be used for adjusting the design of our bike. Bidirectional load test was first recognized, I think, in Brazil in 1970s. Then in the 80s, Dr. Osterberg in United States has recognized the need for using jacks embedded into the body of the pile, and he developed his Osterberg cells, and then he has established the load test company, I think, in the 1990s, and then since then the development of using the O-cell or Osterberg cell method has been very much in practice. More than 30 years of experience. The company Load Test, which is now Fugro Load Test, actually, has contributed a lot and has developed the procedure for using instrumented piles along with the O-cell system, and it is nowadays known as the bidirectional load test. So this is an old photograph showing the Brazilian company. It's called Acros, which has invented their system for using the O-cell or the bidirectional system in the old days. So the pile in this case is divided into two parts, the upper part and lower part, and the hydraulic jacks are embedded within the body of the jack at a certain selected level, sometimes at the toe, sometimes within the body of the pile, and the jacks are activated from the surface after grouting the pile. This is a schematic of a bidirectional load test where the cell is located at the toe of the pile, and we can see once the pile is, of course, concreted and hardened, then the cell is activated from the hydraulic pipes that are an hydraulic system on the surface, and then the jack is pushing the upper pile upward and the lower soil downward. Then the reaction is contained within this system, and the upper part is pushed upward and the lower part is pushed downward. And we have telltales to measure the displacement or the movement of the pile toe as well as the upper plate of the hydraulic of the O-cell jacks, and we also measure the movement at the top. Okay, and this is not instrumented. This is just, you know, any pile without internal instrumentation. This is what typically we get from the OCell tests. Then we get the load, applied load by the hydraulic jack is plotted on the horizontal axis, whereas the displacement of the upper part is plotted positive upward in the vertical axis, and the movement downward for the lower part is plotted pointing downward in millimeters or in inches. And this is what we get is a loading versus displacement. Then we have the final unloading, okay, and this is the typical procedure, okay. We will be very lucky if we can get a similar pattern like this, where we have equal displacements generating at both sides. Okay, sometimes the load representing the upper part is slightly corrected to accommodate the buoyant weight of the pile. So sometimes the load here is slightly less than the load on the lower part, but it's not important for heavily loaded testicles. Now, when instrumenting a pile with vibrating wire gauges, it is desirable to record strain, and this is very important comment, very important to record the strain and temperature, because the strain gauges already measure the temperature and record the temperature. Typically in our testing in practice, we only start to record the strains before the test, before applying the load. But it is desirable to record the strain and temperature from before the gauge is inserted in the pile, before and after concrete is placed, during the hydration, frequently during the first 24 hours, and then spaced out, and several times a day, or so before starting the test. It is particularly important to record the loads and strains during the weld breaking event. Weld breaking event is that, you know, when we go to the previous slide. Here, when we install the lower cage, okay, then we keep some bars, you know, connecting the upper and lower part, and these are typically welded, okay. So once we put the lower cage down, okay, and before concreting, we cut these bars. So this is called the weld breaking point, okay. So here we have to measure or to record. We have to record the load or strain and temperature in the vibrating wire gauges at different events, not only at the start of the test. Nowadays, we have data loggers, so there is no problem to fix the data logger and connect it to the strain gauges once the strain gauges are connected to the steel cage, and just keep these records for a few days, so that we can get the load history in the strain gauges and temperature history before the test is done. And this data is important for us to know if there will be any preload existing in the pile before the test starts. Bidirectional cells has been used also in driven piles. In this case, this is, you know, like a hollow cylindrical concrete driven pile. Of course, after driving, the OCell system is installed and grouted to the place. This is an H-beam that is installed in a pre-drilled hole and will be grouted, of course. So this is the OCell is installed, and this is lowered down, and then the pile is grouted. So it's the different applications of the OCell are possible, not only in one. This is also another photograph of Fugro load test large diameter pile. This is a typical steel funnel is made to allow for, you know, concreting with a trimmed pipe down. So this is just a guide for the trimmed pipe to go through the plate systems in order to make good concreting for the lower part of the pipe. When the pile is instrumented, then the results will look something like this. So we have the upper shaft and we have the lower part or the toe. If the cell is at the toe of the pile, then we get something like that. So this is the toe. If it is somewhere above the toe, then we get another curve representing the lower part of the pile. In this case, the shaft load has been corrected for the effect of the weight of the pile, so it is slightly shifted to the left. And this shows the displacement. And at the end here, we have reached 100 millimeter displacement, and there was unloading. Whereas for the toe, okay, there was some lag before the toe resistance start to take place, and then it followed like a linear relationship. Okay. Then if we, of course, from the strain data, we can calculate the axial stiffness, ESA, and from that we calculate the load at different levels, and this will give us the distribution of the load as we see at different stages. And this will be the blue curve showing us the actual head down relationship, load distribution at the final load, which is around 16,000, okay, if the pile is loaded in a head down fashion. Okay, but what is the red curve? So the red curve is a simulated curve, is a flipped result. Okay, so here the bidirectional load distribution as measured and as flipped over to show the equivalent head down distribution. The red curve is the curve fitted in a unipile calculation applying effective stress analysis with the target beta coefficients indicated in the right. So as we mentioned that from the strain gauge data, we can establish our TZ and QZ curves, which are simulating the actual behavior measured from the test, and we can adjust our beta parameters for the different layers so we can make a very accurate simulation represented in this case by the red curve. Okay, so this is what we call the flipped results. But the blue curve shows the actual results, which indicate that we are very accurately simulating this result. Okay, now in practice, how we get the result and how we get the equivalent head down load movement curve. So the typical data we get from a bidirectional load test is shown by here. We have the movement of the upward part of the pile, and this is the movement versus load of the lower part of the pile. Okay, and then we get the equivalent top down, the equivalent head down pile. So as if the pile is loaded from the top, we need to sum up these results to get our relationship. How we do that? It's typically this is given by the testing companies, but it's very important that the engineer, the consultants must be aware of how this is happening. To do that, okay, we divide or we define points on the curve, like shown here, point 1, 2, 3, 4, 5, 6, etc. These points represent different displacements, okay, specific values of movement. And on the lower curve, we define the same points for the same displacement values. So point 1 in this case, for example, measures 2 millimeter, and point 1 for the other curve measures 2 millimeter. Then we calculate the load corresponding to point 1 on the upper curve and the load corresponding to point 1 on the lower curve. Let this be Q1 and Q2. So Q1 and Q2 give me 1 point on the head down equivalent curve. So point 1 here is giving the same displacement, but the load is equal to the summation of point 1 on the lower curve and point 1 on the upper curve. And we do that for the different points until we reach point 5 here. Okay, because the actual curve here has been, the test has been stopped here. Okay, so this is the maximum net load from the O-cell test. Okay, so the test has been stopped here. So we cannot extrapolate the data after 0.5. So this is our equivalent head down test up to 0.5. Okay, but the lower part has shown that we have more displacement. So in this case, we have to do some kind of extrapolation. So here to make the summation again, I have to extrapolate the upper curve to give me similar level of displacements as the lower curve. So here you can see 0.12 corresponds to a displacement of about 60 millimeter downward. Then we extrapolated. The dotted curve here is just an extrapolated part with 0.12 is about 60 millimeter. And we continue the summation and we get this curve. So this is the solid line is the actual measured data, and the dotted line is the extrapolated part. This has to be shown clearly in the test reports so the engineer will understand how this extrapolation has been done, whether this has been done carefully, whether this has been done in adequate manner or just, any extrapolation. It's very important to show that. Not only that, so if this is our curve, that we have just extrapolated, okay, we have summed the upper and lower curves and extrapolated down. We know that the head down pile or the pile loaded from the top will show more shortening, more elastic shortening than the pile loaded in the bidirectional method, particularly for the upper portion of the bidirectional test. This is because the soil near the O-cell is much more stiffer than the soil near the head of the pile. So if the pile is loaded in a top-down method, it will show higher elastic shortening than what has been indicated by the measured displacements of the upper portion of the bidirectional test. And this needs some further correction. This correction is usually given, or the method or approximate method for doing this correction based on some assumed friction distribution is given in the appendix of the test reports, which you can look at. It is generally accurate. So if it is, checked against, like methods like finite element simulation and so on, it shows that it is practically suitable to do that. But in general, in the loading test reports, you will see that you have what is known as, like they call it between brackets, the rigid pile head down or equivalent head down curve, and then the corrected head down curve. The corrected head down curve is just the rigid pile curve in addition to some calculated elastic shortening to account for the head down loading sequence. And of course, the dotted part is just the extrapolated part. So it must always shown as solid line. This is the measured data, and this is the extrapolated data. So that the engineer can have some kind of evaluation of how this has been done. Now, a better method of doing the extrapolation and the simulation, if we have instrumented pilot test, is to focus on our TZ and QZ curves. As I just mentioned, okay, we can calculate from our instrumentation data the unit shaft resistance and the movement versus the movement, and we can plot our TZ curves for different levels. Okay, so this is level 1, level 2, level 3, depending on the test results. Sometimes we did not reach the maximum side friction, like in this curve and in the red curve, which represents, I think, the toe value here. Okay, then we have to do some extrapolation. This extrapolation can be taken as conservative because it represents only few parts, particularly the parts away from the jacks. Okay, and in this case, we can do such extrapolation. Once we do this extrapolation, we can fit theoretical functions to represent this plastic behavior of our functions, okay, for different levels and for the side friction as well as for the in-bearing. And then we can use that to simulate the O-cell first of all, and then to simulate the head down behavior. So the O-cell here, you can see the simulation, how accurate using unipile after selecting proper TZ functions for the different intervals. And you can see that for the in-bearing as well as for the side friction, okay, the blue points represent the measured values, whereas the red line represents the simulated curve. And from this analysis, we can get the head down curve. So this represents the toe, this represents the shaft, this represents the head down. And for our simulation, we can extend our analysis to any level of displacement that we have based on the functions that we selected. Whereas the blue curve shows of course, this is the uncorrected OCEL equivalent head down test. This is just an enlargement of the same slide, but here what we want to show, this is, the upper part of the file. This is the behavior of the upper part of the file. And if we just plot it in this scale, so we have the displacement on the horizontal axis and the load on the vertical axis, we can see that, the dotted line here, the black curve is the measured upward curve, which is here in blue, okay? And the upward test measurement as simulated. So if we simulate this with the red curve, you can see this here represented as a green curve, okay? But after applying the correction, as I mentioned, for the elastic shortening to represent the head down loading sequence, then the load will be, or the test curve will become this red curve. So this red curve represents the as in head down test. Okay, so it's important because it makes a big difference if we don't do this correction. Okay, then it's important because in defining the capacity or understanding the behavior, it makes a big effect. Fortunately, in our testing practice in Dubai, the testing companies, they already include the corrected curve in their reports. Residual force. Residual force denotes to any force that is existing in the pile shaft before the load test starts, and it can come mainly for driven piles, mainly from negative skin friction if there will be ground subsidence around the pile before the test happens. Fortunately, for board piles and for board piles that are installed in stable grounds, the residual forces are very small and typically they are ignored. If you want to know more about residual force and some examples of how it is evaluated and can be assessed, it is advised that you go to the red book of Dr. Fellenius. He has a very clear chapter talking about that. But talking about bidirectional test, bidirectional load is not sensitive to the existence of residual forces in the shaft. Okay, and typically it is ignored and it's not significant, particularly for board piles. Now, the last part of the presentation is to show some case studies, and we will show the first study is for a project in Dubai. The project here included two preliminary test piles, 1200 and 1500 diameters. One is 39 meter long and one is 44 meter long. It's in Dubai Creek Harbor in Dubai. The loading sequence is just 20 equal increments of the maximum test load. Then there was a holding period for 12 hours. Then we have unloading, and the results are shown. The movement of the upper plate and movement of the toe and movement of the top of the pile and movement of the top plate. The comments of Dr. Fellenius here is that the holding period following the test is not important. So this is just not important. So we can stop the test here. So this is not important at all. It's just confusing. The second thing, because our displacements that are reached during the test, particularly at the toe level, are very limited. So it is recommended to increase the load, or once we reach the maximum, or we plan for 20 increments, 20 equal increments, once we reach the final increment and we still didn't reach failure of the upper or lower parts, the displacements are limited, then we can go for more increments until we reach either failure or reach the maximum capacity of our jacks, and then we can stop. So there is no problem to exceed 20 increments there. We can even use less number of increments as per Dr. Fellenius' recommendation. Also, in the data that he has noticed here, the load, as you can see here, the lines are not straight lines, which means that the load was not held constant during the holding period. Holding period was like 15 minutes for every increment, but the load was not held very much accurately constant during the holding period. It has little effect, but it's important to take care in practice. What I want to mention is that sometimes we are restricted by the diameter of the pile, because with the diameter of the pile, there is a maximum number of jacks and maximum capacity that we can include. And in this case, we have a restriction that we may not be able to increase the loading even if we don't achieve high displacements in these cases. Maybe we need to test shorter piles, and maybe we can divide our piles into two short piles, one representing the upper part of the rock and the other one is representing the lower part of the rock, in order to achieve more displacements and to get better quality results that can be more accurately simulated. This is the data as presented, okay, from the data that we have, and this is, you know, the 1200 millimeter pile. This is the 1500 millimeter pile. This is the strain gauge level that is closer to the jacks, okay, and for this one as well. And as we can see, okay, this is for the upper and lower parts, okay, and as we can see, it's a good matching, and it's almost getting linear relationship. So it's, you know, like good accurate data. Now, if we take this data, which is close to the jack, and we plot the tangent stiffness, okay, we see that we have high fluctuations, which indicate that the data quality can be improved, can be better. Maybe we have to look at the results of every strain gauge and to see if any of the strain gauges has to be cancelled, so we can reduce this fluctuation. But in general, we can get the relationship for our linear stiffness, for our axial stiffness, and we can get the secant stiffness based on that. Actually, for this case, we get high secant stiffness, which can be improved actually in our next practices. From the data, as we mentioned, we can get the load distribution for the upper and lower parts. In this case, this is the location of our cell for the 1200, and this is for the 1500. And from this data, we can get the force for the top loaded pile, okay? And this is the load distribution. What we notice here is that nothing has been mobilized at the inverter, as we expect typically here in Dubai. So because it's a long pile and very small load has been transferred to the inverter, and this is mostly because of the very limited displacement at the top of the pile that has been achieved, and accordingly our designs will be mostly based on ignoring inverting, which adds to the conservatism that we have. And this is the simulation we did with Unipile. So these are the TZ curves, okay, or the load versus displacement curves for different strain gauge levels, okay, which has been simulated by functions and extrapolated. Here is showing the lower part. This is the upper part. This is TP1, the upper strain gauges. and this is for the lower strain gauges, which shows better performance. Okay, and here, you know, for every actual data, which is shown as dotted curves, we have a simulation data curve, which is mathematically defined. And for in-bearing, we have ignored the in-bearing completely, and this will show our simulation extrapolated by Unipile. So here you can see that we have really simulated very accurately. This is the upper part, the upper plate with extrapolation, and this is the top of the pile with extrapolation. This is the lower plate with extrapolation, and this is the toe level, toe movement with extrapolation. Here, toe movement with extrapolation. And from this, we can get the top loaded curve, the head down curve, okay, showing this. And this is our design working load. As we can see, this is the maximum load measured by applied by the O cell. So this is the load that we get from the O cell, and we can see our behavior, even ignoring the in-bearing, we are still in almost linear behavior. If we extend based on the TZ curves that we have simulated, we can get this curve, and this can be our extrapolated portion. Okay, so from this curve, we can decide what is the so-called axial capacity of the pile, and we can improve our working load. Not only that, we can now change the diameter of the pile, we can change the length of the pile, and we can get better scenarios for our design. Another example, and then I will stop after this one. This example is from Vietnam, where a barrette of 2.8 meter by 0.8 meter in size has been loaded with two bidirectional cells. Two tests have been conducted. One test is 65 meter long barrette, and the other one is 85 meter long barrette. So the OCell test can be conducted on barrette piles, not only in circular sections. In this case, the sequence of loading has included an unloading and reloading. So we have two loops, okay? And these are the actual results that has been obtained for the first test and for the second long test. And this is also the load distribution where we got for the short pile, 65 meter, and for the long pile, showing the location of the OCell. And from that, we can also get the head down or do the simulation. If we do the simulation, again, from the data, we can simulate the OCell curves, and we can make our judgment about the accuracy of our simulation based on this. And then from that, we can get the head down curves. I'll stop here and we'll open for questions because I think it's a long presentation. So thank you for your patience and thank you for your attendance. And we'll open for questions and answers now. So I'll open for the questions. I have here one question. From one of the strain measured loading tests, we observed modulus as high as 4 times the theoretical E of the concrete of strains of stress levels in the range of 15 to 30% of concrete strength. The measurement made in the top 2 meter length, not embedded in soil, is used to back calculate E. So if I understand that the test data, the strain data, has been used to recalculate the modulus value, but the modulus value was found to be much higher than the theoretical value based on the concrete strength. And of course, this is not correct because the assessed value from the strain gauges must lie within the range of known modulus ranges. So we know that for good concrete, the modulus can be around 30 megapascal, 32, 33, 35 megapascal, and it depends on the strain. But we cannot, predict values, for example, greater than 40 megapascal. So in this case, we have to relook at the accuracy of the strain data, because the procedure is, as just explained in the presentation, that we have to plot the strain versus the load, and we can get the relationship between the axial stiffness, either secant, and prefer to plot the tangent stiffness. So if you can share the data with us, we can have a look at it and see what has gone wrong with that. The question says, my question is whether this is common. Yes, it is common, but we have to pay attention to the accuracy of the strain data. If we are using secant stiffness, we must make sure that we are starting from zero actual or true zero strain. Otherwise, the data has to be corrected. So I advise that you plot the data in incremental stiffness, and then you can compare. But definitely, if the value is very high, there's something wrong with the strain data. Another question, Mr. Ahmad Shihab. In practical, the both piles have a different area of reinforcement along the pile. So what we should do to evaluate strain gauges using tangent method? Well, the tangent method does not consider the area of steel. If you want to use the formula that I just presented by introducing the modulus of steel, area of steel, and modulus of concrete, area of concrete, then you have to use the actual steel percentage or area at the particular level of strain gauges. But if you use the strain gauge data, then what you need is just to plot the strain versus tangential stiffness, and you get the combined stiffness of the pile. If you want to use the formula, then we advise also that you must do a caliper log test so that you can make sure that the area of the pile is well represented, because sometimes the area is at least 10 centimeters, sometimes is larger than the actual area of the pile, and this makes a big difference. I hope the answers are convincing. If you have any more questions, you can just email it to us, and we will be, of course, very happy to answer. Another question. Could I get the reference for the strain correction used for modulus calculation? Yeah, the webinar is recorded, of course, and the recording can be there. And I think a PDF version of the presentation can be distributed. But you can go to the red book of Fellenius. He has very detailed description of how you can calculate the axial stiffness, either incremental or secant stiffness, with many examples. So you can go to the red book of Fellenius. If you tag to the website www.fellenius.net, you can find a list of his papers and publications, and you can find the answer there. You're welcome. Mr. Ahmed again. What if we do not have a strain gauge near the top of pile? How we calculate the correct tangent modulus? In this case, it's maybe difficult because you need to create, the strain versus the axial stiffness represented as Q over epsilon. So you need the value of Q. So if you don't have strain gauges near the top of the pile, so in next test you have to advise that some strain gauges has to be placed near the jack level. Sometimes when we do testing where we have our piles are socketed in rock, then sometimes we don't put strain gauges within the upper sand part, which is a wrong practice. So we must have usually, and this also gives you calibration of the jack, actually, because the jack sometimes is not instrumented with a load cell, and you are measuring from pressure gauge. So in this case, with the strain gauges available close to the jack, you are getting also some kind of calibration or validation of the results. Thank you very much. I think we have exceeded the time for the presentation, and we have answered the available questions, but definitely we are open for follow-up on the email or by direct contact even. And as I mentioned initially, Dr. Fellenius will be personally happy to elaborate on any of the points that I may not have the opportunity to clarify properly. So thank you very much, and I think we close here. I would like to remind you that the Tea Time Technical Talks will be every first Tuesday every month, and you will receive notifications by email if you are a member. And if you visit the DFI Middle East website, you will be able to see the details, and we encourage your participation and thank you for that. Thank you very much.